Arguably, one of the most important concepts in all of physics are vectors. It has range of uses from special relativity, general relativity, all the way to kinematics and even in quantum mechanics. So let's understand. First, let's define what a vector is. A vector is defined as an arrow through space. And vector that starts at the origin and reaches to a point let's call A is known as a position vector. Yes. Okay. Where that is the x-axis and that is the y-axis. One unit of the x-axis is known as I hat, while one of the y-axis is known as the j hat. So, if we define A's x-coordinate to be 4 and this y-coordinate to be 3, we can also define A as a vector 4i hat plus 3j hat. Like that, we have defined our first vector. So now, let's go to our next part. Vector addition. Okay. So, it goes as follows. First, we have our grid as usual. And now we have a position vector. And another position vector. Let's call the position vector 2 and 1's coordinates 4 and minus 1. And its y coordinates are both 3. To add vectors together, we have to take the bottom arrow and we have to move its tail to the top of the second one, like that. This new vector will be defined from going to the origin to the end point, where the vector's value would just be the addition of 4i hat plus minus 1 j hat, or small error there is j hat, and the other is 3, so will be 3 j hat, while the other would be 3i hat plus 3i hat, which is 6i hat. Oh, small problem there, small mix up on the units, but I hat was meant to be j hat while j hat was meant to be I hat. But now we have defined our first ever vector addition, which is great progress, as now we can start doing simple things. This is known as the dot and tail method, which is one of the methods of two methods. This is another thing to note is that the two vectors you are adding are supposed to go in the same direction. If it's clockwise, the other will be a rebel and go anti-clockwise. If your two original vectors were to go anti-clockwise, then the other vector would go clockwise, being the rebel that it is. Okay, now let's go into the parallelogram method, which is really just the same thing, but in a more fancy way that some people might prefer, or more suitable in some math questions. But in physics, they're essentially the same. So we have our grid as normal, and we have our position vector, and another position vector, which both have the value of I hat 3, and the other is j hat minus 1 and j hat 4. We put this vector, the one with minus 1 j hat, and put it up, and we put the other vector there, forming a parallelogram. Then we'll connect the two ends of the parallelogram to form our new vector. When this is similar to the dot and tail method, but it might appeal to some other people, or more specifically, as mentioned before, apply to some maths question, maybe in IGCSE. But overall, this is the essence of vector addition. Now, we should get into its opposite, vector subtraction. Well, since addition and subtraction are just inverses of each other, the process is pretty similar. Let's first define a vector. which has the x coordinate 5 and y coordinates 4, and another vector with y coordinates -1 and x coordinates 2. We know this as A and B. If A minus B is our vectors that we want to subtract, so let's define A minus B to be equivalent to vector x, the vector we want. So A equals B plus x. This simplifies the problem to, well, what other vector can be added, so B plus the vector makes A, which is just this vector, which would be x. Now we have to move this x vector to the origin to find the different values of x, which are just 5 and then 3. Okay, so now we have got our first vector subtraction. We can move on to an essential part in electromagnetism that is slightly more complicated, which I'll try to explain more simply, but it might be slightly hard. The dot product. The dot product, let's define a box moving in the direction of vector A. Okay, so the dot product basically is how much a vector B helps its motion, how much extra force is given by vector B. Okay, so let's say vector B is in the same direction as vector A. Then it will give its maximum possible aid, as all of its concentration is towards the x-axis. So using the formula, which we will, is AB cos theta will just be 1, so it's AB, its maximum value. But if B were perpendicular to A, it will change its y-axis, up, down, up, down, up, down. But in hypothetical conditions, it will not affect its x-axis, which is what we are trying to affect with this extra force, since x is the direction of motion of A. And as you can see here, y does not affect it. Okay, so we'll write the formula AB cos theta, where theta is 90, and we get 0. And this is, well, when it makes a perpendicular with A, which is quite intuitive. But now, let's say we were to change it a bit and add a vector in the opposite direction of A. Okay, let's draw the vector, which is B, which is going the opposite direction. Then what would the value be? If we put AB and define this as 179 degrees for unknown reasons, because why not? We have AB cos 179. Since cos 179 is negative, our answer would too be negative. So in that case, the 8 is negative as it opposes the direction of motion, and thus the dot product is negative. So like that we understand dot products. Now for cross products. This is truly a very, very complicated concept, and although it can be very helpful, its understanding is less intuitive. Let's imagine we have a screw and, well, a wrench. Sorry for the bad drawings, but in physics, drawings don't matter as long as there's some degree of accuracy. Let's say the force is exerted in direction A, and then from the center of the screw to the wrench is B. The cross product would just be AB sine theta. Well, at least its magnitude, cause the cross product actually is a vector. This means that it should have another direction for it to be a vector. So to know its direction, let's first draw a 3D grid, and we have this vector going there and that vector going there. The new vector should be perpendicular to both of the original vectors in order for it to be, and this would be the direction of the cross product's vector. So this is the direction, this is the magnitude, and, well, that is basically what a cross product is, with the direction and magnitude. With that, we have this solid work. And we can now start to do some cooler things. We have defined vector addition, vector subtraction, dot products, and cross products. And now we have to enter a concept which is very, very common in kinematics, which is known as vector decomposition. This concept will become a very norm when you continue into physics, which goes as follows. Let's say you have an arrow which is defined as the velocity. Let's say it's a ball getting thrown and this is its trajectory with initial velocity being v. Now let's make a triangle with the angle theta being subtended by the normal and the vector. Okay. Now for this part we'll need to use some simple trigonometry. So sine theta is equivalent to the opposite over hypotenuse, where the hypotenuse is just v. So sine theta equals the opposite over v, and thus we can define the opposite to be sine theta multiplied by v. So now we have decomposed its x-axis, its y-axis. Now we'll use a similar concept but to get its adjacent line, which is cos theta equals adjacent over hypotenuse. Cos theta equals adjacent over velocity, so adjacent equals to cos theta times velocity. And like that, we have its x-axis to be velocity times the cos of theta. And we have successfully decomposed our vector into its x direction and y direction. This will simplify problems greatly in the future, where we will not need to deal with multiple directions at once. So this is basically what vector decomposition is. Now let's give a quick summary of the lesson or of vectors in general. Okay, the summary would be let's have a vector A and another vector, then the vector addition would just be from there to there, the tail to the head. Addition of vectors, very simple. Now we have this, where this is the line that we want, as this is vector subtraction. Let's define that as A and B, and we want A minus B. So this is vector subtraction. Okay, now we have our more abstract concepts of dot products, which we can imagine with a box and some formulas which could be proved. AB cos theta, where we have a box moving in a direction, and then we have to see how much help is given with our vector of force, which is B. This is known as the dot product, which is written as A dot B. And our final operation to be given to a vector is the cross product, which is defined as a vector which depends on the distance, it has a direction, and also the direction vector of the force. And the magnitude and direction are both needed for it to be a vector, and its magnitude is AB sine theta. This is known as the cross product, which is written as AXB. Finally, we have the vector decomposition, where we use some trigonometry and the angle theta, so that side is v sine theta while the bottom side is v cosine theta. And this is decomposition. Done.